We've tried it quite a bit.
You hear us. Good. So it's a pleasure to have here Professor Bufetov, who will talk about determinantal processes and reproducing kernels. So
thank you very much, and thank you for your patience, which was severely tried. So let us start with some basic examples. And I want to start really just with example of the sign process. So this is just a measure on space of configurations on the line R. Space of configurations on the line R, which is space of infinite arrays of particles without accumulation points, like this. So I consider a subset of R. X has no accumulation points. No accumulation points. This space is a Polish space. This is a Polish space. Why is it Polish space? Let us briefly consider this question. Why is it Polish space? Because this X is itself a measure. Hugo, do you agree with me? This set is itself a measure. It's atomic radon measure. Yes? So since it's atomic radon measure, we will consider measures on measures. So this X I can bijectively assign eta X, which is just sum of delta X and X. And consider the space, consider just usual vague topology on this space of measures. Vague topology. Okay, so now I would like to consider measures on this space of measures. So measures on this space of measures. And what do I mean by measure on this space of measures? So how do I define a measure on, so it's called a point process, so point process is a measure, is a Borel probability measure on the space of configurations. On the space of configurations. Okay. And I consider just how do I define such measure? How is it possible to define such measure? To define a measure, I need to define expectations of some functionals of this measure. And expectation of some functionals of this measure, it is convenient for me to consider multiplicative functions. Multiplicative functionals. And so what I mean by multiplicative functionals is very simple. It's just psi g of x is product of g of x and x. Another way of saying the same thing is that I can consider additive functional SF of x. And here I consider exponential moment of this multiplicative function. So I consider e to the lambda s f of x is of course a multiplicative function. Its product is psi e to the lambda f of x. Okay, so this is the way. So if I assign expectations of all multiplicative functionals, then I also assign a measure. Why is this? So let me make a remark that point process is uniquely defined. Point process is uniquely defined by multiplicative functions. Defined by expectations. By all expectations of psi of g. And why is that? This is because just if I take, in fact, some joint distribution of some so-called occupation numbers, so I take hash a of x is cardinality, number of points of x in A, of x in A. So then, if I take the exponential, so this is an additive functional, this is obviously additive. So if I take expectation of the exponential of this, then I get multiplicative functions, then I get essentially generating function of these joint distributions, and this precisely tautologically defines my measure. So measure on space of configurations is tautologically defined by these occupation numbers, expectations of these occupation numbers, I would better say joint distributions of these occupation numbers, and joint distribution of occupation numbers are given by multiplicative functions. So this is, excuse me, I should write E psi. Yes, so generating function of the joint distribution, of the joint distribution. Okay, so this much for abstract remark that multiplicative functions determine the measure uniquely.
But so the mean of all a's must be the whole line?
No, not necessarily. Just A is disjoint. No, I'll disjoint. No, it doesn't matter. No. In fact, these are bounded sets. So just, your question is why joint distributions of such things determine the measure uniquely. For one thing, one can take this as definition of Borel sigma algebra. Just Borel sigma algebra is just sigma algebra generated by these occupation numbers. But as I said, this is Polish space. So Polish space has its natural Borel sigma algebra, and then there is a simple and pleasant exercise that these two coincide. So in fact, it is Borel sigma algebra in the sense of topology. To have Borel sigma algebra, you don't really need topology. So Borel sigma algebra in the sense of topology and Borel sigma algebra in this sense, they coincide. Okay? Makes sense? Okay. So just multiplicative functions determine the measure uniquely. And now I'm ready to give a definition of determinantal point process. So point process is determinantal. Point process P is determinantal. If expectation of multiplicative functional is given by Fredholm determinant. So here, in fact, one needs a little bit of care. And since this is important for what I will continue with, let me be, in fact, careful. So when I write this Fredholm determinant, it's not, in fact, Fredholm determinant. So let me say it's regularization of Fredholm determinant. Let me be a little bit careful because it's important for what I will continue with. So let us recall. So Fredholm determinant is defined for operators with finite trace. So for example, as product 1 plus eigenvalue, something like this, for operators with finite trace. But it is also possible to define a regularization of Fredholm determinant, which is like this: e to the minus trace a determinant 1 plus a. So the advantage of this regularized Fredholm determinant is that it is defined for Hilbert-Schmidt operators, not just for this one. It's defined for Hilbert-Schmidt operators. So I start with operators of finite rank, and then this quantity is well defined for operators with finite trace. But this quantity, in fact, it is defined like this, but in fact it is defined for such operators for which neither the first multiple nor the second multiple are defined, but it is defined for operators with finite, with finite Hilbert-Schmidt norm, with finite Hilbert-Schmidt norm. But now it will be very convenient. So let me explain the difficulty. The difficulty is that it is very difficult to check that such operator has finite trace. In fact, I don't know how to do it. It is, on the other hand, very easy to check. So this operator is not self-adjoint. It's difficult for me to check that it has finite trace. It is, on the other hand, quite easy to check that it is Hilbert-Schmidt. Just one computes the sum of the square of the integral of the square of the kernel. So it's immediate computation. So it is also observed that I can define trace of, so let me write trace in quotation marks of g minus 1k as integral g minus 1 k xx. So such trace in quotation marks can be defined even if the operator does not have finite trace. Maybe it does, maybe it doesn't. So I write determinant in this sense. I write determinant 1 plus a is exponential of a xx dx times the second determinant. And please observe that here I only need existence of such integral in principal value, for example, and that a be Hilbert-Schmidt operator. So this is quite important nuance for what follows. And why is it important? You will see in a moment. You will see in a moment why it is important to extend the class of operators to to extend the definition of determinant to this set of operators. We still have multiplicativity property in this situation. And now I'm ready to formulate one of the first main results. So I will consider this talk is mainly devoted to the sign process. So and the sign process is determinantal point process with kernel. So sign process. Is determinantal point process with kernel S of xy is sine pi x minus y over pi x minus y. So this, please let me say one thing. It remains an open problem. In fact, it remains an open problem what kernels K induce determinantal point process. It's open. There do, however, exist sufficient conditions for this, and a sufficient condition for this is when K is projection. K is projection. So if K is projection admitting a kernel, then the formula that expectation of multiplicative function is determinant 1 plus g minus 1k induces a determinantal point process. So, and in particular, this example is the sign process. Okay, so let me observe. It is important for what follows that the kernel of the sign kernel is a quite special kernel. In fact, what is this kernel? SF. I take Fourier transform. I restrict to minus pi, and I take the inverse Fourier transform. definition of sine kernel. But in fact, any kernel which is a projection, so this is clearly a projection which has any kernel which induces a projection induces a determinant point process. This is theorem of Maki-Soshnikov, Shirai, and Takahashi. Okay, so now I'm ready to formulate first main result of this talk, and this is an analog of Sigel's theorem for such sine process. So it is possible to obtain in this situation analog of strong Sigel's theorem. So let me introduce a little bit of notation. So analog, in fact, it is a little bit more than Sigel's theorem. It is analog of Borodino-Kunkov-Geronimo case formula. Of Kunkov-Geronimo case formula. So, and what is this analog of Borodino-Kunkov-Geronimo case formula? This is the following statement. Just I am interested in multiplicative functionals under the sine process. So I take function g, and I write g to be exponential of, maybe I write g to be exponential of phi. So, and I write phi is equal to phi plus phi minus. And phi plus and phi minus belong to Dirichlet space. What I mean by this is that phi plus has Fourier transform supported in 0 plus infinity. Phi minus has Fourier transform supported in minus infinity 0. Minus infinity 0. And both phi plus and phi minus belong to Sobolev 1/2 space. So in these considerations, I need Sobolev spaces. So let me write. So I need Sobolev spaces and I need Sobolev seminorms. So I write Sobolev seminorms. Sobolev seminorms. So phi square HP is for me the integral lambda to the power p phi hat of lambda square d lambda. So, and I need that phi belongs to phi plus, phi minus, all of them belong to h1/2. h1/2. Okay, so these are my assumptions, and now I'm ready to formulate the analog of the no, excuse me, just one more thing. I also write h equals to exponential phi minus phi plus, exponential phi minus phi plus, and I also need continual analog of Hankel operator. So let me write it here. Continual analog of Hankel operator. Continual analog of Hankel operator. So I will write it like this. H of H is equal, well, exactly what you think it is. H S plus H of H F of S is equal H F of T F of T dt. From 0 to infinity. This is just analog of usual Hankel operator. Something not clear about notation? Please ask.
No, I was just looking at the definition of Sobolev seminors. It shouldn't be 2p in the integral modulus of lambda. And h1 is the first derivative, right?
Thank you very much. Thank you very much. Thank you very much. Yes. Thank you very much. Yes. Very good. Very good. Excuse me. Yes, you're absolutely right. Of course it should. Yes, thank you very much. Thank you very much. So, thank you very much, yes. But Hankel, okay, so one I read with mistake, one I read correctly. So Hankel, I think, thank you very much. Hankel, I think I wrote correctly. Yeah. Yes, thank you very much. Okay, so, and just, yes, of course, in fact, 1/2 is half derivative, so it's lambda to the power 1. Thank you very much. Yes. So, okay. So now, with this notation, I'm ready to formulate the result. So the expectation under the sign process of the multiplicative function of psi g is equal to, okay, so there is term exponential excuse me, 2 pi integral of phi. So let me write like this, phi. Then I have the following, one more notation I need, for function phi. I introduce function phi tilde by writing that phi tilde hat of minus lambda is equal to phi hat of lambda. So tilde is just taking the minus in the Fourier transform. Okay, so now I have phi plus phi minus tilde 1/2. Of course, this inner product corresponds to the same norm. 1/2. Okay, so this is the Séguin term, and now here is Borodino-Volkov-Geronimo case term, determinant 1 minus chi 2 pi plus infinity chi h. H is this one. H is here. This is H. Please observe that if phi is real, then H has absolute value 1. Because if phi is real, then phi plus and phi minus are conjugates of each other. Then phi minus phi plus is purely imaginary. And H has absolute value 1. But in fact, we need this formula not only in situations when phi is real, because we also need it in situations when, for example, phi is some imaginary number times real function. Okay, so and now I write Hankel of H inverse tilde and chi 2 pi plus infinity. Okay, and this is the formula. So, what is convenient about this formula? From this formula, we'll have some interesting consequences, which I will now also explain. So, but what is unusual about this formula? So, please observe. So, the expectation of multiplicative functional. So, there is this Séguin term. Then there is this mistake. Just it is if, as I said, phi is real, then these operators are conjugates of each other. So this is the adjoint. This is the adjoint of this, and so this quantity is between 0 and 1. Okay. So let me now draw some corollaries from this formula. So let me draw corollary here. The unusual, so let me say, as I said, my point process is measure on space of configurations. This measure is by definition stationary. By definition, because kernel is invariant under translations. So it is by definition stationary. Please observe, however, that, so of course it satisfies law of large numbers. So a number of points in configuration in large interval is close to length of this interval. So next question is, does it satisfy central limit theorem? So, and we shall see that it does, but and in very interesting sense. So, in fact, let us look at this. Let us look at this formula, and let us take phi. Let us introduce on space of functions the group action of the group of dilations. Ta of phi is equal to phi, like this, group of dilations. Yes. So. Group of dilations. And please observe that. So if I take phi some function, well, of course, there is this term which precisely corresponds to law of large numbers. If I take phi and I start to dilate it, then this term increases. But let me take some phi which has average 0. If I take function phi which has average 0, then, as one can easily see, so if I take now G post-composed with Ta, and I assume that this term doesn't exist, so this term is equal to 0, assuming that this term is equal to 0. Please observe that this term does not change. Because Sobolev 1/2 norm is invariant under dilations. And this term, we shall see that this term goes to, in fact, goes to 1, but I will explain this a little bit later, but let me point out even now the following quite remarkable fact, that the expectation, let me write it like this, expectation of lambda fixed, lambda can be real or complex, sum, so S, I wrote it S of phi. So phi is some function, something like this, right? Let's say like this. So I dilate it, so it becomes something like this. And these random variables, so what do? I take sum of my random variables in these intervals. Essentially, these are number of random variables in this interval minus number of variables at this interval, a little bit smoothed on the sides. So, for example, if I had Poisson process, this would have variance square root of n, square root of the length, square root of a. But here the variance stays bounded. This is just a corollary of this formula. Here the variance stays bounded. Yes, because this is 0. So the particles under the sign process, they cancel each other out so carefully that the variance stays bounded. This is a theorem of Soshnikov building on previous work of Johansson. So Soshnikov building on previous work of Johansson. So just Johansson observed this for eigenvalues of random matrices, in fact. That just, in fact, using so for in the case of circular unitary ensemble, one can use just, in fact, the classical Sigas theorem, classical strong Sigas theorem. So, but let me point out this quite unusual fact. Let me again emphasize this quite unusual fact that the particles cancel out so carefully that just the variance of this quantity becomes bound. So let us look now at this term. So now I will prove, in fact, Soshnikov limit theorem. So in fact, let us look at this term. So when I consider H, so again, Hankel operator itself also does not change. Hankel operator, there is the same dilation. At the same time, this operator, so there is this 2 pi here. So this operator does change. So in fact, if I write chi to pi plus infinity, so let me write in terms of Hilbert-Schmidt norm by infinity. Let me write it like this actually. Of H, Hilbert-Schmidt norm, is equal, it is quite easy to check, is equal to integral from 2 pi plus infinity. In fact, the same expression as for the Sobolev 1/2 norm. So lambda, if it's only in positive, so I don't need to write absolute value, lambda h hat of lambda square d lambda. Lambda h hat of lambda square d lambda. Okay, so, but integral is from 2 pi. And so, if I have if I have expectation of this quantity, so now I need to if I'm interested in expectation of this quantity, I need to consider chi to pi plus infinity h of h, but corresponding to the function, so in fact h ta h. So I need to expand h. And one easily checks, in fact one easily checks that the Hilbert-Schmidt norm of this one will in fact be integral of 2 pi a to infinity of lambda so which goes to 0. So it will just cut the, doesn't make sense, it will just cut this Sobolev norm. A verification must be made that in fact the function h belongs to the Sobolev 1/2 space, but it does. So please, I ask you just to believe me about this. Okay, so this much for that. And then we obtained the desired, central limit theorem of Soshnikov for this. Furthermore, from this formula we obtain a little bit more. We obtain, in fact, so let me write this. So corollary is that the speed of convergence, corollary. So from this formula, using it quite naively, speed of convergence speed of convergence to the normal distribution. So speed of convergence. So let me write that this converges to normal distribution. So this is Soshnikov's theorem. Normal distribution with 0 and the norm, in fact, one can see here, the norm phi square. So speed of convergence in Soshnikov's theorem, central limit theorem, is O large of 1 over logarithm A. So let me explain why logarithm A. This is just upper estimate, maybe it's not optimal, but it's best I can do. So why do I obtain logarithm A? So in fact, I have this, so to obtain speed of convergence, I need to consider, obviously, characteristic function. So I need to consider I lambda. So at this point, I would have here exponential of I lambda phi. Exponential of I lambda phi. So exponential of I lambda phi. And lambda will have to compete. So please observe that lambda in H will go on top. So H will be exponential of lambda something. So A will have to be counterbalanced, will have to counterbalance the influence of lambda. So A will have to be so big to counterbalance the influence of lambda. So precisely this will work if lambda is log of A. And this precisely gives this O large of 1 over log of A. So this is corollary on the speed of convergence in Soshnikov's theorem. Okay, so let me formulate 2 more results and finish with that. So this result is in fact used in the proof of the following. So I need to erase something. Let me erase here. So as I mentioned, the realizations of sign process are very similar to just natural integers. A realization of sign process, one can think of it as integers which oscillate a little bit. So now the Kotelnikov theorem gives a connection between integers and reproducing kernels in Paley-Wiener space. Okay, let me say this. So let us recall that precisely Paley-Wiener space is the space. Paley-Wiener space is the space of functions such that the Fourier transform is a minus pi pi. So it's precisely the range of the sign kernel. And of course, the reproducing kernels sine pi minus k pi. So k and z form an orthogonal basis, form an orthogonal basis in Pelley-Wiener space. Orthogonal basis. Orthonormal even if one normalizes. Probably in Pelley-Wiener space. Okay. So this of course corresponds to the fact that e to the I k theta k and z form orthogonal basis in of course L2 of minus pi pi. And this is just the Kotelnikov. Okay. So now let us look at this statement from point of view of sign process. So, in fact, there is a theorem of Gauche. Which says that that for almost every configuration x under the sign process, the set e to the I x theta is a complete, so it's not orthogonal anymore, but it's a complete sequence, in L2 of minus pi pi. Is complete in L2 minus pi pi. Equivalently, the set of reproducing kernels, is complete in Pelley-Wiener space. So this set, this family, is complete in Pelley-Wiener space. Okay. So, by the way, this statement is true in very general, in generality of all determinant wide process, that realization of reproducing kernel along almost every realization is complete in the corresponding space, and this is joint work with Xu and Chanov. But this is just a statement of completeness. So now it is natural to ask question: how much defect do I have? So it's complete, but is it complete with an excess? If I remove one particle, is it still complete? So the sequence of natural numbers, it is complete and minimal. So it is complete, but if I remove one natural number, then I get subspace of codimension 1. So the question is, in this case, if I remove one particle, is it still complete? The answer is yes. If I remove two particles, is it still complete? The answer is no. So this is main result of this talk, which I'm now ready to formulate. So, okay, let me formulate this theorem. Let me formulate it here. So, okay, I erase this. So, theorem. Just the sign process has excess 1. Process has excess 1. That is to say that, so in other words, for almost every x, so this is theorem, so for almost every X, the set